Okay, I think we'll get started. So today we're going to do some motion in one dimension. We're just going to start with this. And over the course of the next few days, with the homework, with some of the in-class work, we're going to get really good at that. And what that means is using our kinematic equations that we developed last time. We have uniform motion, which is relatively simple. This is the constant velocity case. And then we have constant acceleration. So that will occupy our time, and we'll be able to do quite a bit of physics under these conditions, because oftentimes something is freely moving, like a hockey puck sliding on ice or a free rolling bicycle. Then we would be in the uniform motion case. And nicely, the motion of an object in the gravitational field of Earth, or any planet for that matter. So if I have this and I drop it, it's going to accelerate in this direction because of the force of gravity. And it turns out that acceleration is constant if we're close enough to the surface of the Earth. And all these problems, we're going to be assuming we're close enough to the surface. And even if we're on a really high building, we're still close enough to the surface of the Earth. And the gravitational constant here is 9.8 meters per second, and it's directed downward, always towards the floor. And so our acceleration then is always a minus g. So we'll be able to do like free motion problems and then motion under gravity. And that's going to actually cover a lot of material. So let's put to work the constant acceleration case for two very special cases. And then, as I said, as we move forward, we'll generalize this so that we can use these equations in any possible case. And by the end of a couple of weeks, well, maybe even 1 week, you should be really, really handy with these equations. Okay, so let's do the example we talked about earlier in the course, where we didn't know how to answer these questions, but now we do because we have our kinematic equations. So we're going to just drop a ball from height h. And we'll put this in a coordinate system, and we'll decide, again, we're free to decide wherever we want to, but a good choice of 0 is the ground, and then the ball itself is at y equals h, some height h. Okay, so we're still pretty general. This is just dropping an object from a certain height. Okay, this will be done under gravity. So constant acceleration case. So we know we are not using this equation. We're using these two equations. Since we're going up and down, let's call that y instead of x. Okay, so all that happens is the x's turn into y's. Okay, so let's write our full kinematic equation just in general. We have it right here, but it's always good to start the problem with one of these equations, right? And then let's plug in what we know. So we go from our picture here, and we know our initial height, our initial position before we drop the ball is at h, so there's h. And our final position is the ball on the ground, so that's 0. So there's two of our variables in this equation. Now what's nice about the free fall problem is we're releasing the ball with 0 velocity. So what that means is that this whole term, this goes to 0, right? So it's 0 here, so this whole term cancels. So we lose a whole term in that equation. Then what's our acceleration? Well, our acceleration is minus g, so I'm going to just change this plus to a minus, and then this is just 1/2 times a, so that's g over 2, right? Minus g over 2, and then we have delta t squared. Okay? Well, let's solve for delta t now, because presumably we may want to know, if we know the height, then we may want to solve for delta t. Maybe we know delta t and we want to solve for the height. Okay, so we could do either that. Let's solve for delta t. So if we get delta t squared all by itself, we'll bring the h over to the other side. That's going to cancel those minus signs. So we'll have 2h. This is going to come up over here, 2h over g. Okay, so take a moment and make sure you check my algebra here. Work that through yourself. And then let's solve by just taking the square root and getting delta t. Okay. Now, so notice one kind of, mathematically, there's two answers, right? Delta t could be negative or positive, because when you square it, it's going to be positive. But then you appeal to the physics of the problem. It doesn't take negative time for me to drop the ball until it hits the ground. So the positive solution is the real physical solution. The negative is called a spurious solution or a non-physical solution. Okay, let's do an example. Let's say we happen to be 10 meters, right? And then it's just kind of a plug and chug. Right? So we would plug in 10 meters into this equation and we get 1.4 seconds. Now we might then be able to go on and use this equation now to answer not only how long did it take for the ball to drop, but what was the speed when it hit the ground, or what was the velocity. And notice, I should have said this earlier. Notice I've taken now in these 1D problems, we often remove the explicit vector arrow on the top because the sign takes care of the vector direction. So for this case, positive sign means going upward and a negative sign means going downward. So we would expect here now, we better get a negative velocity. Okay, so we plug this in. A is minus 9.8, so that's where the negative comes from. Here's our time, and so we get minus 14 meters per second. So it's hitting the ground at minus 14 meters per second. Okay. All right, well, let's add to this just a little bit, and let's do a leap problem. So when we get down, we load our legs, right? We extend. All that is where we're providing some of our own force from our muscles to get ourselves going in order to create a launch velocity, the velocity at which we leave the ground. So we are going to take the physics from here to here, right? So that the instant our feet leave contact with the ground, there's nothing more we can do. It's all just this kinematic equation, just an object, that's us, moving under gravity. Until we land, right? Then we land and we cushion our landing, right? And then our muscles act to slow us down or decelerate us, and bring us to a stop, right? So this part, right, and this part, that is something we control. We're doing something there to get our launch velocity and then to cushion our landing velocity. But in between, we are just an object floating through space, right? Under the constant pull of gravity. So what we're going to do though here is use some symmetry. Right? And so in a sense, what goes up must come down, right? And there's no real difference from going up compared to down other than the direction. So we can sort of think of this motion. I've given it some width here, but really we're just going straight up, straight down, right? We're not jumping forward. So we're one dimension, just straight up, straight down. We can cut this in half, right? And say, okay, whatever it took to get up to h, that's what it's going to take to get down from h. Okay, so the rise time is going to equal the fall time. And furthermore, whatever velocity we took off from this direction, let's think about what's going to happen. We're going to take off with a certain velocity. We're going to go up and up and up, but we're slowing down, right? And then we reach the top of our jump, and we're kind of hung there for just an instant in space here. And then we start to speed up coming downward. And so we start with 0 velocity, and then we hit the ground with the same velocity that we came up with. So we have some symmetry there as well. And so the launch and the landing are the same but opposite directions. So we need a minus sign here. So if launching is a positive, which it will be because we'll be going up, then landing is a negative, as it will be because we're going down. So basically what we've done is we've taken the leap problem and we've just made it a free fall problem. And then we just have to keep track of what we're actually calculating. So from our free fall problem, we know how to calculate the time of the fall, right? So we've done that already. And so then the time of the whole leap, at the time of the leap, is just delta t rise plus delta t fall. So we just multiply by 2 because these are equal to each other. T rise equals t fall. So our whole equation here just has an extra factor of 2 there. All right, well, what's our landing? V landing, right? That is going to go back from here, just like we did over here. So if our V final, right, it's a free fall problem now, so V initial is 0 minus G delta T. So V landing here now, right, is going to be minus G delta T. But delta T, which delta T do we use? Just the fall, right? And so we get this, and that's going to be negative. So we would multiply by a minus sign, so that negative would go away, and that would give us our launch velocity. Okay. So let's do an example. Let's say we have a launch velocity of 10 meters per second. So something jumps off the ground at 10 meters per second. This would be more than we could do as a human, but let's say something pops off the ground or leaps off the ground with 10 meters per second. Then we can rearrange this, right? So we're using this equation here, except with the negative sign. So we have 10 equals 9.8 times the square root of 2h divided by 9.8. We don't know what the apex of that leap is going to be. That's what we're going to calculate. So these are all numbers except for the h. So we've got the 4.7 meters. So check my arithmetic there, make sure I've got that right. Okay, well then we have our formula for the whole time of the leap, right, which is just up here. We already calculated our h, so we say the whatever it was that jumping there was in the air for almost 2 seconds there, 1.9 seconds. Okay, now these are two special cases, and they're important special cases, and they illustrate the idea of symmetry. But what we're going to want to be able to do, and we will be able to do this very shortly, is not necessarily go up and down. So let's say we start on a plyometric block and we jump up from there and land on the ground. So in that case, we've started at a different place than we finished, and we can't use the symmetry then. So in that case, we're going to be completely general. And once we get to that point, then and you're getting the problems right, then you've mastered your kinematic equations, which is really where we want to be in about a week or so. So get lots of problems on this in the homework, in the practice, in the quizzes, and in some of the things to come. And what's great is the work we do now, it'll automatically take us to when we start talking about 2 dimensions, which is coming up soon. We're going to talk about ramps next, and then we'll talk about 2 dimensions, and it's no different than putting 2 one-dimension problems together, and those 2 one dimensions are uniform motion and constant motion. So the key work now in the next couple of days is to really get these equations down.